Good morning. This is the official start of the fall 2024 lecture, and this will eventually become a YouTube video when I post it up. Right now in the class there are YouTube videos, or in the course website there's YouTube videos from fall 2022. So those are entirely in place, and I guess we'll just take a look at that right now so you can see what I'm talking about. This is the new website. The old one is likely still there, but they keep telling me it's going to go off the air like any moment. I've been waiting for this to happen for about 2 months, but it has to do with a lot of factors. So don't try to look for the old one with any intent. You'll find it maybe it's still there. I don't know. It might be the way they help me with this website. But this particular course is in pretty good shape right now. And they helped me design the page, actually. So what I'm talking about here is if I was to follow this link, or you look down the corner, it says YouTube. So they're all going to be on YouTube. And I guess since I'm stopping here right now, I'll just ask you, since YouTube doesn't charge me anything, I can make a channel that's fall 2024 and just start creating another parallel stack. So I'll leave all of the 2022s up there, then I'll just start adding. Does that sound okay? I mean, I wasn't sure whether I was going to do that or not, but my son, who works at my family's church, does screencasting and all the other stuff with the church. He uses YouTube all the time, and he's definitely an expert on YouTube and Facebook, you know, real-time streaming and all that stuff. So I've been asking him to help me because I've never done YouTube. I've watched YouTube a lot, but I've never created my own channel. And I'm not excited about reading my comments either. Actually, I don't plan on reading my comments because do I have to? I don't think I have to read my comments. So we'll go back over, well, as long as I'm in the website, I'll just say the things that you'll be wanting to grab onto will be under this tab. The course syllabus, which I just gave you, is linked here. And if I make changes to it, I'll repost it. And this is another thing I'm trying to learn how to use. I'm a fan of being able to post new documents and have the date and time show up right next to it. But the plugin, which is how WordPress works, that IT put on for me, they don't give me much powers. So if I need things, I have to get them to do things for me on this site. They put it in, and it's using UTC, Universal Time Coordination, which is in Great Britain. It's basically what used to be Greenwich Mean Time. And then they couldn't figure it out, and I said, you can come down and grab, well, I don't have any more syllabi to hand out because I only made 6 of them. So you must be a walk-on, or somebody's a walk-on, but we'll get you one. At any rate, the plugin manufacturer didn't even test their plugin. I'm telling you this story because as engineers, what is something that you have to learn how to do when you're assigned a project? You have to be aggressive and go after things. If you're working on something that somebody sold you to use in your design and things aren't working out, what do? You call them, right? Or you post or do something. So I asked IT to give me the vendor for the plugin that they installed, and I just wrote them an email post and I said, here's my issues, and they said, made up some excuses like, we're going to look into this, and then eventually they came back and said, guess what? You're right, it doesn't work. It doesn't display in the time zone that you set it to display at. So they hopefully will resolve this sometime during the next few weeks. I really don't know. But I put the UTC next to that because that just lets you know. It's a shift of like 7 hours right now. But it changes, right? Do you know why it changes? They don't go on daylight savings time. So when we come off of daylight savings time, then will be different by an additional hour. So I can use Slack though too, and that brings up why I want to use Slack. Some of you have signed in to the accounts. Somebody here whose name I don't know, and I'll need your email for sure so I can give you an invitation to join Slack. Slack is sort of a competitor to Microsoft Teams. Slack is older than Teams, so it's a little bit more, it's not quite as packed up with stuff. I mean, I actually like Slack better. I originally started using it during COVID. Students in my classes then wanted me to go to Slack. And hopefully that's fading in the rearview mirror for most of you, but some of you were freshmen then, or what? Does anybody want to admit what they remember about spring 2020 when all of a sudden we shut down? It was a panic time for sure. So this is what I went to though, and Slack, I'm using the free version of it, so I might as well go through that right now. Once you join the workspace, then I will send you a message, because it will message me like it did right now. Somebody just joined. So, oops. No, that's a graduate student that's going to meet with me later. But at any rate, your names will start appearing on here. And then the way Slack works, very much like Teams does, is you have channels. And we have channels up here for Modern DSP. And I wrote a message on this August 17th, actually, when I first posted something. So you can join that channel once you're in this workspace the workspace is called DSP Com Courses. I created this quite a few years ago. And the way the free version of Slack works, if you go to some channels and you see that fuzzed out stuff, it's because I'm not paying for it. So it's got a window that moves along on a 3-month interval, and it doesn't delete it, it just doesn't let us use it anymore. I'm okay with that, because I don't think, as we start erasing at the beginning, we're going to be bothered that much, right, if you're engaging me. And so the channel for the course is where I can announce things and you can bring things up for all of us to read. The individual channels that we have, called direct messages in the terminology of Slack, those are one-on-ones between just me and you. You can form a 3-way channel if you want to with other people in the class. If you wanted to do that, it's possible to do that. But the one-way channels, or direct messaging channels, is how you're going to submit homeworks to me by just dragging and dropping a PDF. If you scan part of it, or part of it's on the computer, I'm going to talk about how you can merge that together. I will pull that off of there and then grade it on my tablet, and then I'll push it back on there. If you need grade updates, I can give you grade updates. I don't use Canvas, so I suppose if I was still a full-time faculty member, I'd have to use Canvas or something. That's what the campus uses now, right? I'm so old that Canvas didn't exist, and when it first came online, it was very unreliable, and I just thought, I'll use my website that I created, and I'll stay with it. But I don't want to make you feel like you can't know what's going on. But I also put up histograms as a signals and systems person. Statistics, probability, random variables, all that stuff is really important to me. And I think to you, and a histogram is important too. If you do homeworks, first homework set, I'll put up a histogram. You can see exactly the distribution of the scores. I'll give you the mean and the variance of, whatever. I do things like that. You have a question?
I had a question. Sorry, I came in late, so you might have explained that.
Yeah, why don't you come down and grab this? I'm wired to my microphone right now. Just come on down and grab that pad. But I don't have a syllabus copy for you right now. But just so I know your name, the white sheet with the pen on top of it. Just sign in.
My question to you was, do you have a specific book that you assigned for this class?
Yes, it's on the syllabus.
And the only reason I asked that is we had a similar issue last semester when the class was not up on Canvas. You can't see the books on tab portal.
Okay. Well, everything's right here under course materials, course syllabus, and I actually have that opened up right here. So It's Oppenheim and Schaefer, which you can get in a paperback form. Have any of you bought it yet? It's pretty reasonably priced compared to a regular. See if this will open up for me. Yeah. That's the book, and paperback prices are pretty reasonable. That's what students were buying the last time I was teaching the class 2 years ago. If I would have been on a sabbatical and not retired from from teaching, I would have been gone all of last year and I would have come back this year. So this is a standard interval I'm familiar with over my lifetime. You know, missing one fall semester and coming back again. But it's a really good book. It's an older book, but it's written by two figures in digital signal processing, one from MIT and one from Georgia Tech. I think they're both retired. I know the Georgia Tech professor Schaefer is definitely retired, and Alan Oppenheim from MIT is most certainly retired. I hope none of them are deceased yet, but you know, that comes next. I'm not trying to sound morbid, but it's just the way timelines work, right? The timeline for our life is what I'm saying. So I want you to have this. I want you to have the problems out of it. And those are what are on my first assignment sheet. Does that help?
Kind of not. So those of us who opted into TAP, we get these books online for free. So if you set up a class on Canvas, we can go into VitalSource and get this book for free.
Okay, I didn't know that they were giving them away for free.
Well, you pay for the TAP, but it's a little cheaper in my opinion if you wanted books online.
Okay. Maybe you have to educate me on it then by sending me something on Slack to tell me how to do it once you sign into Slack.
Yes, sir.
Okay. Because I know it's out there, but I generally never logged into it myself. So I know there's lots of things they do to help you out, but I actually thought that this paperback price of around $51 or whatever, it was pretty good. This is a heavy book. I didn't even bring it with me because I rode my bike today. It's about that thick. I mean, it's pretty heavy. It's got a lot of stuff in it. And all the DSP books used for this sort of course are big, pretty fat books because there's a lot to this subject. Not that we do it all in one semester, but you have it as a reference then. So, okay, back to where I was. I was talking about the use of Slack. So a bunch of you have now, nope. The guy I'm meeting with after this is writing me a lot of messages. So. And the other thing about Slack that I happen to like, it's not extremely complex, it's not extremely big and fat like Microsoft Teams is. I don't know if you would have rather me use Teams, but I have to use it in the work I'm doing right now at a company, and it's just so, it gets to be so overwhelming. There's too much to it. Slack is a lot leaner. It's very easy to have it on your cell phone. It's very easy to put it on your tablet or PC, and if it's on your cell phone, like for me, I can see messages that come from you guys. I call it getting slacked. You know, if I hear a ding, I know somebody's just messaged me, but I can more quickly try to respond to it. Not instantly. I might be out walking my dogs or doing anything like that, but I can attend to it more quickly. And what we can do once we're in Slack, up at the top, those headphones there allow us to do what it's called a huddle. And a huddle in the free version is just between two people. So if we're using our direct messaging channel and one of you wants to ask me a question about homework, you show me something and then I might say, do you want to talk about it? And we can do a huddle right then and there. We can not only message, we can talk voice-wise, we can share screens and that sort of thing. So that's pretty handy to me. I realize Teams does that too, but this is just a little bit leaner in my opinion. I have to use Teams where I'm working right now, and I had to use it in the previous job. I never had to use it here, though. I wasn't forced into using it. So that's kind of my sales pitch for the use of Slack. If you don't want to do it, you still have to get me the homework. You could email it to me, of course, but I think it's pretty reasonable. Since we're talking about emailing, when you do scan, you maybe probably take pictures with your cell phone. Try to take a look at what you do before you actually send it off to me, because I can go blind, or than I am, trying to read your stuff. And I have a big, 12-inch iPad that I bought in 2019 because of some confusion with the Apple Store giving me a credit, and I had to spend it on something from the Apple Store. So I bought the biggest iPad I could, and lo and behold, a couple months later, COVID hits, and now I'm really glad I have this iPad. Have you ever had things like that happen? It's like you spent some money and kind of were like, why did I spend all that money? But then, and I play music, so I can read music off of it too. So I play in a jazz band. I play bass trombone is what I play. And I'm teaching myself tuba right now as well for another ensemble. So you got to have hobbies, right? And music and signal processing definitely go together, in my humble opinion. You might disagree, but if you like singing, I sing, but I like playing my horn. So, any other questions before I jump back over to something else? So I've gone through Slack a bit, and I think you'll get very much used to it.
I looked too much, and the book that is recommended off of the TAP website is the same one. So you should have it.
So Amazon's connection is okay, or?
Oh yeah, what I mean is the one that the bookstore now, as we do, is providing that same book. So
Okay. So what should you do? Or at break time, maybe you want to talk about it. If I don't have to use Canvas, I don't want to use it. So that's kind of what I'm not sounding super lame, but I'd rather just not get into more phrase of things than I have to.
You have to set it up or ask staff if you can embed it into that, what you are using.
Okay.
A link to it.
Yeah, Eva, our front office staff person, retired at the end of the spring semester, and yeah. I guess they finally got approval to hire a replacement, but when I talked with Dr. Kalker in the middle of the summer, he said, we don't have any replacement. They're not going to give us another staff person. But then I've heard, when I went to lunch with Dr. Trimboli and Dr. Platt a few weeks ago, they said that it had come through. But things are pretty shaky right now in our department. Very shaky, actually, because there's nobody in the front office. Okay. So let's just start going through this introductory set of lecture notes, and then as time permits, we'll go into the actual first chapter, which is chapter 2 in the notes. And I'm trying something different. I'm going to just use the Microsoft Edge browser since it's got editing tools, and I have a stylus from this tablet, as opposed to an app that I used to use, and now, well, it's not working as it used to. I made it, not a mistake, but I said to IT, can you upgrade my machine to Windows 11? So I haven't really checked out every app after the upgrade went on my machine. So.
Before we dive in, I was curious, since you're definitely promoting the lab for this class.
Yeah.
Could you describe what we...
Yeah, I will when I get there. Yeah, I actually got a piece of hardware down here right now. So, yeah. No, it's good. I am going to talk to you about it. So first off, I have this cover page, and it shows a picture of some signals and a system block diagram. So I had a really nice demo of this, an interactive demo of this running in Julia, which is a competitor to Python, which of course are both open source competitors to MATLAB. And 2 years ago I advocated Julia a lot, but I'll probably show you some demos, but I'm probably going to stick with Python mostly, but we'll be talking about that too. But at any rate, so discrete time signal processing, you've had 3205 or some equivalent to that, where you've seen N2610, where you've seen discrete time signals in systems. So the input X goes into this block, and inside the block that represents the system, I'm showing you the magnitude response in the frequency domain, and I'm showing you a pole and zero plot for the underlying system. These are two things we're going to use a lot in this class. We kind of have three main domains of viewing signals and systems. We have time domain, frequency domain, and then Z domain. Frequency domain is Fourier transform from the time domain, and Z domain is Z transform of the time domain. And those are all parallel to continuous time signals and systems where you have a function of the continuous time variable t. You take the Fourier transform to get the the spectrum of the signal or the frequency response of the system, and then you have the Laplace transform generally used to get in a system function domain where you have poles and zeros from that. And those are things you've seen in, like I said, 2610 and 3205. I'll keep reflecting back on that all along, and I'll just say that if you're interested in a quick review and you want to spend about $20, I have a book I wrote over 10 years ago now called Signals and Systems for Dummies, which was a fun experience, a laborsome experience, but I decided to write software for it in Python, and that turned into a big package in Python, which we'll be using in this class. So that was probably the most important thing for me. It got me exposed to Python. It got me this t-shirt when I went to the conference one year. And this is a distribution called Anaconda that I recommend still to this day. Miniconda is what we'll be talking about later. And that was fun. I mean, open source software communities. I would go to the conference for SciPy, which Scientific Python sort of branch off from pure Python, and get to see a lot of people from different domains that use Python, for example. Not just engineers. Engineers are kind of the nerdier bunch of the crowd that goes to a Scientific Python conference. You've got people like biology people, people that do weather. I mean, just you name it, geophysics. Everybody uses scientific tools, though, to do things. And certainly you've all heard of machine learning, AI, and that sort of stuff. That's all hovering around essentially everything, and we're inside of that domain. Those of us that do signals and systems, we're alongside that, and it's sort of ever fluctuating. But at any rate, so here's the characteristics. We see a signal going in, it's a sample or discrete time signal, and then you see a signal coming out at the bottom. So what do you suppose is happening there? What does the signal at the bottom kind of look like? It's got a transient where it's starting up over here, but after that it appears to become very regular. And what does that appear to be from your knowledge?
Sine wave.
Sinusoidal. How many sine waves?
Just one.
Just one, right? And what do you see up above? You can't really see in terms of sine waves how many it would be. But it's certainly more than one, right? But it appears as if there's some periodicity in there. I don't remember exactly how I created this. Agreed? Approximately. So the system now shows frequency response that has a very deep notch or null at some frequency, and it's got 0 dB gain either side of that. So what you see the system is doing is it's removing something. It's nulling something out, or annihilating something. That's a good term to use in signal processing. I realize annihilation is used other places, but this is in engineering terms, so it's safe, it's friendly. It's just we're going to remove a signal we don't want, a jamming signal, let's say. And that would lead to apparently that sinusoid. So another conclusion you can make, if there's more than two sinusoids going in, that notch would only be able to remove one of them, right? Approximately so. So it must be that there's only two sinusoids. Is that a fair conclusion? I mean, this is part of being a signals and systems person. You'd want to prove it with maybe some more modeling and simulation, but in this case, that is what's going on. And the design of this notch, I gotta watch my cord. The design of this notch has got zeros on the unit circle, and we're going to be learning or relearning that it's the angle from the positive real axis up to here that corresponds to the frequency where the notch is sitting. In other words, this angle in radians corresponds to this frequency in normalized radians. This 0.5 would correspond to half the sampling rate in an analog and A to D converter type DSP system. And this pole is put behind that zero, and what it does is it allows you to control how sharp the notch is. I look at that notch shape and it's kind of like a thumbtack. If you take a thumbtack and push it down, it's got a point, and you can make it get narrower or wider. Another term that's used in RF would be Q, right? Quality factor. What the loss is in the resonator or something if it's an analog circuit. Of course, in DSP, we don't have to worry about finite Q in an analog circuit where we have loss in materials like metal and capacitors and so on. We just have to get a high Q, we just have to have precision in our numerics to do that. But I heard some people talking about microwave measurements lab. I'm a fan of microwave circuits from way back when, because the course that Dr. Song teaches was a course I developed way back when. I originally developed that course. So I like all this stuff, but you do have to focus, though. You're not going to do everything all the time in industry. You do everything every now and then, but you don't do super well because you just can't be an expert on everything. So without the demo of that, I'll just move on. So what is this big enough, or should I do this? Too big, right? Is that big enough? Okay. I mean, I'm not used to this flexibility with this high resolution screen. It's kind of impressive. A few weeks ago, my wife had some major back surgery, and a few weeks before that, she said, I think we should get a new TV, so we bought a 4K TV. And we didn't even think about it, but we got to use it to watch the Olympics, so it was like, that's the reason why we bought the TV, was to watch the Olympics, which it was amazing. I mean, the 4K channels are simply amazing, so this kind of makes me think of going from an HD TV to 4K, which a lot of you maybe did a long time ago, but we hadn't bought a TV for over 12 years, so. And it still worked perfectly. It was a plasma screen TV. Had to pay to have it. Had to pay Best Buy to take it and do something with it. And then they told me, your new TV is not going to last that long. Most of you have been there before too, right? Newer stuff, consumer electronics doesn't last as long as older stuff. They just, as the salesman said, they realized they weren't going to sell enough TVs, so they made them too well, and they have to make people have to buy a new one. I don't know if that's absolutely true, but I think in appliances that's kind of true. Okay, so what is contemporary or modern DSP? That term, that name of the course was on there when I started teaching in 1984 at UCCS, so it's a long time ago. But modern is relative, right? Each new year we can say it's modern. I mean, so every time I teach the class, there's new things that have come on the scene, and we're always trying to stay bringing up new characteristics or attributes. But one of the things that I'm not going to be able to do that very well. The theory pretty much is at the bottom level. It's very solid. It's been around since the 70s and maybe even a little bit earlier than that. It's the technology and the applications that do keep changing. And this class is mostly focused on the theory and the math modeling side of things. So there's obviously more more exotic theories that are being developed all the time, but the core basics of the theory are staying the same. I'll talk some about the expected background, and then where you can go from here after this course. And I'll have a lot of question marks on there because I'm not full-time faculty. I'm going to project and say, if we had this new faculty member, this faculty member would presumably go on and do this, this, or this. And I'm going to show you a roadmap of what those courses might be. But that roadmap is my roadmap. So one of the things when you leave the work here, I had to say, if everything gets thrown in the garbage can, so be it. I mean, I don't have control over that. And if the new person wants to not do that anymore, so be it. I mean, I would argue against that, but you know, I really don't have the right to demand anything anymore. We'll talk about exactly what we're going to do in the class, and I'm really big on computer analysis and simulation tools in and outside the class. And I'm kind of fanatical in a way because I do so much work in industry and I use lots of different tools, and I like doing things well, and I like making customers happy. And I just started a new job last Thursday at another company, Emergent Technologies. Has anybody heard of them? Because they do come to interview. They actually were bought by another company, a consortium company called ARCA that has a bunch of technology companies. So I had worked for them and had contracts from them many years ago, but I'm actually an ARCA employee, consulting employee, and then I'm working for another division called Tethers, which is a division that's in Washington. But I get to work out of the office here, work from home. That's where I was working now when I wrote my Signals and Systems for Dummies book. I was working at Emergent. There'll be a couple of computer simulation projects that you'll be doing as well. And in spite of having the lab to work with the real hardware, like the board I'll hand around here later, the computer simulation project does have some real-time DSP in it using the Jupyter Notebook and Python together with Pi Audio. And Pi Audio is a package that I extended with a module called Pi Audio Helper, so you can actually do real-time DSP in your laptop. You can put up widgets, you know, controls, sliders, and other things, and you can use your PC sound system to do audio analog I/O through your PC. And you'll get to play with that. And if you live alone, you'll be happy. You can make noises. If you have a spouse around, they might not like some of the sounds that you'll be producing, but it's quite a bit of fun, actually. I like being able to do things hands-on. The lab does more of that, and it does it using microcontrollers and programming in C, is the way it works right now. But you will get exposed to the Python version of it in one of the projects. We'll also talk about policies. So quickly, theoretical foundation, late 60s, early 70s. There were a couple of texts in the very beginning. Digital signal processing, that's the book that I studied out of, not in the 60s, but that's the book that was the active popular book when I did my graduate degree. I didn't do DSP as an undergraduate. It really wasn't that available. I didn't do it for my master's, but I came back when I got my doctorate and did DSP then. And that's Oppenheim and Schaefer. So that book is still in print. So the book we have, Discrete Time Signal Processing, for this course was created by those two guys later as the more modern and contemporary version of what was started way back when. So just to let you know, that's why I'm bringing that up. There's quite a legacy. There was a couple other guys that wrote a book too, published in '75. I guess they were both published around '75. So our book is, like I said, it's this one. I was fixing typos in this and didn't get them fixed, missing a space, and favorites, what I meant here. a newer text that I got probably 2 years ago, and that's on the syllabus. I think there's a link to it on the syllabus, but you can look at Amazon. It's more modern. It's very MATLAB centric, so that's one of the things I have against it. It's kind of like, I think open source is better. Oppenheim and Schaefer doesn't tell you about any language to use to model and simulate. It's just, here it is. So, but it's, I'm trying to remember where he's from, the author's from, but it may become the more standard book. I'm not really sure, because Oppenheim and Schaefer published a new version every 10 years approximately. I got to teach out of all 3 of those while I was here, and the 2010 version is the one we're using, and there won't be any more, I don't believe. I mean, another thing about life and timelines, right? You think about it, you can't keep doing that. Some people want to, but most people just say that'll be the end. Sometimes, though, authors do hand their legacy over to some young faculty member or somebody in industry that wants to continue, and then they inherit, the updated editions and things like that. You've probably seen that in your lifetime here. Ever noticed where you see a new author is added and you see an older author that's maybe even listed as deceased or something? That happens some, but not that much. So what is the technology? Remember I said there's theory, technology, and application. So the technology side, we have DSP chips and architectures is what I list here. And DSP chips and architectures is kind of maybe pretty generic sounding, because for a while there, back in the earlier days of DSP, there were microcontrollers that were specially created for doing real-time signal processing. Now, those aren't quite so popular. Probably the more popular thing that you'd find for doing that would be ASICs that are made by Xilinx that have the ARM cores on them plus the fabric, FPGA fabric. So you can put your algorithms up into either side of that architecture. And I did that when I first left here working for a company. I'm not a VHDL or Verilog coder, but I got put in the middle of a project and I was using Vivado, which is a tool for doing Verilog and VHDL development. And I learned how to use it fairly well. I didn't write all the VHDL and Verilog code, but I could simulate the design and I could create test vectors in Python or Julia. And then eventually it was on the board and I was on the bench with the board and I was interfacing to test equipment and it was working. I mean, did it work instantly? No. Were there pain and struggling? Yes. But, that's kind of the way it goes. And the sub-bullets, their integer fixed point just reflects what certain types of DSP implementations involve. Like cell phones traditionally have been small, lean, mean devices, very power efficient, and the DSP algorithms in cell phones have traditionally been mostly fixed point, because fixed point math is fast and it's efficient. It doesn't require a lot of real estate to do fixed point math. If you're going to do floating point math, you have to have big registers for multiplications and more power consumption. I mean, Xilinx came along with the DSP slice many years ago, which is available in their FPGAs. And if you run on the ARM core, of course, you have access to floating point. And floating point implementations, though, are advantageous because you can rapidly prototype them. You can go right from MATLAB, Python, or Julia simulation models, and then you can get that ported into, say, an ARM core device, which would run on that particular core inside the FPGA, and then part of the algorithms would be in the FPGA fabric. That seems to be, in all the things I've been working on lately or been around for the past 5 or more years, everything is a combination of an ARM core device, usually, and an FPGA. And algorithms are partitioned between the two of them. Sometimes it's just the ARM core device. So that leads to the next topic, actually, software, tools, and so on. So I mentioned FPGA a bunch, but so that's hardware description languages. When you're programming on the ARM core side, doing fixed point or floating point, a popular language there would be C and C++. Mostly C++ is what I've done. For this company that I originally worked at, I've got stuff that's actually flying in space right now that they let me write it. I wrote it, I translated it from my prototypes in Python, or maybe it was Octave, which is an open source version of MATLAB. And then it got put into classes in C++, and then the overall systems programmer or embedded systems developer took my modules and put those into the ARM core side of the FPGA, and they perform certain functions for a military type application, government application. FPGA side is more specialized, like for example at Emergent, their technology has been based on using Intel cores for ground station equipment, satellite ground station equipment, but they will have a front end board that has the FPGA hooked up to their RF front end, and nowadays it's called the RF SoC that you might have, RF system on a chip that has a number of high-speed A to Ds that can sample at, say, 6 gigasamples per second and have multiple channels of that. I worked on a project for a few months for a company in California that involved building a base station for 5G. And I was just looking at system architectures and coming up with ideas of undersampling and using IF sampling. We'll go through that in here. We're going to talk about how you can take a signal and sample it not using the Nyquist low-pass formula. What you learn in 2610 and 3205 is, what do you remember? You have to sample at greater than twice the highest frequency. Remember that? Well, it turns out you can get by with much less than that, and that's called bandpass sampling. So we'll be talking about that. In radio design, you can take advantage of that. In a software-defined radio, you can undersample and pull out some nice tricks to keep your sampling rate from being so high. And that's what the RF SoC definitely takes advantage of, and there's lots of integrated structure in there, so some of the filters that are needed to process with undersampling are actually implemented right on the chip without them having to be instantiated into the fabric, let's say. I mean, let's just think, we think systems in this class. We're systems architects, systems modeling, simulation. That's what I'm in a sense training you to how you think, how you should think, and that's always a part of every project. There's always a systems person somewhere. Now maybe that systems person will do the FPGA design too, but so we think about how to have certain architectural capabilities in some of our subsystems. So if it's a software-defined radio front end, it will have filter banks and digital down converters, what it's called, to take a signal at one frequency and digitally down convert it to a baseband signal from an RF signal, and do that using some analog components and filtering in the discrete time domain. And a digital down converter is exactly what it is. It's all done in the discrete time domain. It has some analog at the very, very front end. And then the rest of that will be DSP after that. And baseband just means the signal is centered around zero frequency. And we'll be talking about complex baseband at times. I realize it's mind expanding to have to think that way, but life is not that simple in signal processing and engineering. It's not just a single stream of samples. It's very frequently a complex stream of samples. But you would say, but why? Where do I get that complex sample from? I get it if I'm working with radio type signals and I'm working from something that I'm taking off of a carrier. I will get what's called in-phase and quadrature or real and imaginary parts. It happens very naturally, and It's huge in radio stuff. If you're just doing audio processing, no, you don't need that. But when you're doing radio processing, you do need that, and it comes very naturally. It complicates your thinking, but our tools, no problem whatsoever. MATLAB, Python, Julia, handle the complex signals, no problem. And then you get really cool things. I'll just mention one thing really quickly. What do you remember from continuous time Fourier transforms? You had a transform theorem called frequency translation. Do you remember that theorem? No?
It was like a year ago.
Okay. Modulation theorem, do you remember that one? Maybe not. Okay. That would have been in Dr. Trimboli's 3205 though, right? That's where it would get taught. I'm pretty sure maybe 2610, but more comprehensively in 3205. Well, frequency translation is one that when you learn about it in the Fourier domain, continuous time signals, you'd say, what do I do with that? I'm going to generate a complex signal when I multiply a real signal times a complex sinusoid. Frequency translation is where you multiply signal times in e to the j omega naught t. In the discrete time domain, when you do that, you end up with a complex signal stream, and that is in essence how you can take a signal that's at a high frequency, say it's way up here, and DC is right here, and you can shift it down to baseband, but then it's a complex signal, but that's okay for communications applications. So you can take it off a carrier, a high frequency signal, and move it down or move it around approximately to baseband. And baseband nominally is at 0, centers everything at 0, but in real communication signals, you're never going to move it exactly to 0. Want to guess why that is? Just thinking in terms of practice. Oscillators, the transmitted signal is not, you don't have a copy of its oscillator locally when you receive it, so you move it down, it's only going to be close. And then the other thing is motion or Doppler. You always have Doppler in SATCOM, you have Doppler in mobile radio, so you get it close. It's within maybe kilohertz or hertz, but you have to deal with that too, but it is of course possible. Pretty cool actually. The work I've done over the last few years, I've gotten involved with orbital mechanics a lot too, just trying to understand how these signals, what the Dopplers are depending upon the orbit and that sort of thing. So I've learned about two-line element sets, and which is in a catalog that tells you how a satellite's flying, and you can use the two-line element set and get a propagator in Python or MATLAB or whatever. A satellite propagator will take from the two-line element set, which is orbital mechanics info, and then you can put a time stamp on that and say, this is where this object is in space, this is its velocity, this is its position, and then you can step the time and have it put into motion. So you typically, like for a satellite, you would get the ephemeris, as it's known. And the most important things from a signal processing standpoint generally are, once you have the ephemeris, then you can get the radial from where you are on the ground in your coordinate system, say Earth-centered, Earth-fixed, out to where that point in space is, and you'll get the radial, and then you'll get the derivative of the radial. So you get R is the radial, right? And then R dot would be the time rate of change of R. From that you can get your Doppler, and you just do a lot of stuff with that. I don't know, does that sound amazing, or just, I mean, it all fits together, trust me, it does. And where did you learn about things like that? Radials, R and R dot. It takes me back to physics. I mean, what coordinate systems, change of coordinate systems. It's not that hard. You just type in the internet and say, I want to do a transformation from ECEF, Earth-centered, Earth-fixed, to maybe a local east-north up coordinate frame, which is what GPS would more or less use. This is where your experience of having a GPS and going hiking and using topo maps and other things, if you've ever done that. But the equations are there, and you can put them in your code, and then you can transfer them. So I've got a project on GitHub that talks about how Kalman filters take the pseudo ranges in a GPS receiver and produce your position on the ground, and that involves some coordinate transformations. The ENU is the one I used there. ENU is east, north, up. It's just a reference frame, you know, east, north, and then up. And it's east, north, up because it also brings in the right-hand rule, which you learned in physics, I think, right? Or maybe in calculus somewhere along the line. Do you ever think about that ever? I think when you're working these problems, you keep thinking, you know, the right-hand rule just not only in electromagnetics or other things. ENU is, you know, east, north. I'm holding it from my frame of reference, but east, north, and then that crossed into that. The third element would be up, right? There's the opposite one, which points down, but the up one, ENU, is the one I used in some stuff that I did. But ECEF, and then there's there's different orbital frames that are either Earth-centric or centered relative to the sun. I mean, all kinds of there's other frames out there, coordinate frames. It doesn't seem like it should matter to a signal processing person, but it sort of does in a way. So you end up getting introduced to stuff like that. Sorry for diverging off there, but every step of the way you learn more about things. So DSP design and software tools, I'll talk about that in a little bit more detail, but engineers use design tools. So we use modeling tools mostly in signals and systems, like I already said, MATLAB, Python, or Julia. You might use some other tools that are out there, but then we'll have C and C++ for prototyping as well, and then hardware description languages, of course, comes into there too. That is not this class, but I'm just saying if you take the FPGA class, or you take, I guess in the fall, it's the, what's the class called again? Dr. Pereira usually has taught it.
Embedded systems.
Well, embedded systems is more off to the side, but it can be DSP in embedded systems, but
I think
VLSI design, is that it?
Dr. Calgar teaches that.
That's the substrate or the...
I think rapid prototyping with FPGA.
Yeah, there's the other one though. What is that one? It's just...
IC design?
No, it's Verilog.
Oh, advanced digital design.
Yeah, advanced digital design. That's where you learn about writing in Verilog. Military projects generally use VHDL still. There's, you know, the languages are similar but not the same. I was taking a crash course on that last fall, or actually a year ago when I was working at this company. But that ties you over so that you can be on a project where there's, say, signal processing, and then there's an implementation side of it. I mean, what I'm doing right now for this tethers company is I'm doing system architecture stuff for a receiver design for spread spectrum. And then there's a guy that's kind of like I'm working in parallel with, who's a implementer. He's implementing in VHDL and in Verilog, the design that will go on the fabric, and it will be part of the overall receiver design. So there's a spread spectrum despreading operation, and that's what I'm working on. But then there's other things in the receiver design to get the data bits back as well. So I generally work closely with people that do the FPGA design, and if you want to understand that better, you would take a class in that, and then you would be more knowledgeable. You can straddle the two areas to some extent. That's kind of what I'm getting at. Or maybe you want to be more on the RF side, so you take microwave circuits, or you take something else to understand the front end and some of the issues with propagation and RF front end stuff. I know on this project they have an amplifier chain that brings the signal in, and they're having some compression problems with that. And compression is just when you have an analog amplifier and you overdrive it. You don't gain regulate it properly with received signals. Then there's the transmit signal chain side. And what else just went through my brain there really fast? Well, yeah, the compression side is something that you can model then in the signal processing side. If you compress a signal, what does that do to a modulated carrier? And that's where digital communications comes in. Digital communications is actually all tied up inside of this too. This class is more the nuts and bolts of what goes on to implement things these days in discrete time domain and algorithms on FPGA and other processors. But what are those things we're going to build using this knowledge from DSP? We're going to build comm systems maybe it's audio systems, maybe it's ADAS, which I'm going to be talking about a little bit later. Does everybody know what ADAS is? Okay, I guess I put a link up in here. I'm not sure where it is down here. There it is. ADAS. Advanced Driver Assistance Systems. It's not just a system, it's many systems now. I get news every day from design magazines for electrical engineers, and ADAS related topics are dominant. ADAS is automotive. Our cars are becoming massive computing platforms, and Transportation Safety Board is mandating certain things to go in cars. And I'm getting ahead of myself, but that's okay. ADAS is, I think I popped this up in here earlier. It's going to bring up another web browser. It can be mundane things like cameras up on your window that see if you're within the lines or not. I have a 2017 RAV4, so it has that system on it, which I can turn on. It lets me know if I jump out the lines. It's got the radar in the front for the cruise control, but that radar, and then it's got the acoustic sensors all the way around the perimeter for backup. If I'm backing out of my driveway, I live on a hill right over here, car racing down the hill, the Doppler gets picked up by that motion sensor and it tells me, look out, there's somebody coming close to you. I mean, that's part of ADAS. But one of the biggest things that's happening is using ADAS type systems to just recognize your situation of cars around you, not just your cruise control. Now, radar cruise control is pretty nice if you've ever used it. Anybody use it?
Yeah.
It has some problems. Mine is 2017, so it definitely gets confused. I'm driving on Interstate 25. There's an exit ramp here, and depending upon the angles, it can get confused, and all of a sudden, it's putting the brakes on really heavily. It's deaccelerating me like crazy. Then that car moves out of the field of view, and then it's flooring the accelerator pedal to bring me back up to speed. That is not cool. Or I'm coming around the corner over where I live by some apartments. There's always a car sitting there, and it will think that I'm going to hit that car. So big things flash up saying you're going to have a collision, and it's a car just sitting there, and it always sits there, but every now and then it picks that up and senses it and says, look out. But in general, it works good when you're driving on the interstate.
For long distance, it's
it tracks, and then the newer systems will let you know that the car that you're approaching is below your set point, so that you know you need to get out into the lane, right? Mine is older. Mine doesn't do that. Mine just slows down, and it lulls you into going slower, and then pretty soon you realize you're going really slow, maybe 45 miles an hour, because you're behind a truck that's only going 45. That's been improved upon. You'll get a little beep. My wife has a Honda. You get a little beep that you're approaching somebody from behind that's not at your set point. It's below your set point. It gives you enough advance notice to say, look over your shoulder. Is there space? You can pull out and get around. But But then there's more situational things coming on board. So it's all, to me, it's all signal processing. It's algorithms that are working with spatial information. And then I was going to show you some more stuff that I got from a TI, Texas Instruments blurb on some of the systems, but this is just Wikipedia right here. I think this is not particularly up to date right now. It's changing. It's changing very rapidly. The radar systems are not just going to be looking forward, they're going to be looking to the back. There's going to be multiple layers of multiple radar systems out there, and then the signal processing off of those radars. If you're into RF and millimeter wave electronics, then microwave circuits it's involved with that. So it's really pretty cool stuff if you can tolerate it. You got a question?
Yeah. So this system, it uses both cameras and radar at the same time?
I think so. I mean, everything is getting fused. I'd call that data fusion or fusing multiple sensors. I'm not saying I know for a fact, but I know that's yeah. And that's algorithms, and to me that's signal processing. People that do it might not call it signal processing, but I do, because it's algorithms and figuring out how to do things, making decisions. Machine learning, of course, is involved. All that stuff comes into play. It's pretty exciting. The older you are, the more of a skeptic you are, and we are giving up control. Every time you put on another onboard system on that's supposed to make your life safer, you're handing it over to something else that's supposed to make sure that you don't screw up. But I think we're all engineers. Can we make things that are just 100% infallible? Unfortunately, we can't. I mean, jet aircraft have bad things happen every now and then, right? But we try, and we're trying to get, in terms of probability and reliability theory, you think about how many nines are in the probability of not failing. So like for an aircraft, maybe it's 6 nines or something like that. It's very close to 100% reliable, but never 100% reliable, right? Are you okay with that? I mean, as an engineer and designer, that's something you just have to work with. You'll be asked, how reliable can you make this? If you're, I don't know, I was reading in the news yesterday, my wife would like to go to Iceland, and did you read about the ice cave collapse yesterday? I have brothers, or one brother that was in Iceland with his family over the summer, and I'm sure he toured an ice cave, but there was a collapse, and I'm sure they're going to say global warming was behind this, but at any rate, people were digging other people out, and one American, all I saw in the headlines, one American tourist was killed when an ice cave collapsed. I mean, I go backpacking, I'm on trails, I do running on trails and cycling. We're always putting ourselves in harm's way. If we don't do that, we're not really living, I don't think. So we can't over-engineer it to the point where we're going to protect everybody from anything. I think we're driven by adrenaline. We get, the more thrill we get out of something, the more we might want to do something that's, like trail running is something my son got me into. I'm not as great in my leg. I've got some joint issues these days, but I thought it was fun. But then I realized you go down on some rocks and you're wearing your shorts, your skin gets torn up very quickly. But if you can fly from one rock to the next, you feel like you've accomplished something. I think that's the way I think you thrive on that. So I said a little bit about tools, but I also have, I'm wondering if a page got deleted here, but I have some key application areas. I think I'm supposed to be taking the break probably. What time is the break time generally? Is it 9:15? The next class starts at 9:15, right?
This class ends at 9:15, the next starts at 9:25.
Yeah, well, this class goes till 10:40,
Yeah.
but I don't know. I don't hear the noise out there. We could take the break now before we start this next topic. Is that okay? And then I'll just roll on from there. Don't go far. I'd like to start by, let's say, 9:20 on my watch. And if you want to talk to me, I'm going to pause my video and... Okay, so we're back recording, and just speaking of the recording, this will just be one seamless recording, and you'll know that we went on break because I talked about it before we went on break, and we'll be back, and then I'll process this in Camtasia Studio later. So quickly here, what are some of the key things that go on with DSP? And this is on the move constantly, but this is actually pretty old, but cable modems have DSP, broadband access. What do we have going in all over Colorado Springs right now?
Fiber.
What's the name of the company?
Quantum.
Well, there's another one. I thought it was only Metronet.
Quantum's going on as well.
And
At least in my area, because I'm
Okay.
speaking to them next week.
I live right over here up the hillside from the Mennonite Church is where I live, but Metronet is what's going in. So that's signal processing stuff too.
Quantum is Eastern Powers.
Okay, so there's another competitor to Comcast, Xfinity. That's the interesting thing. And I'm worrying about my yard being torn up when they run the fiber up, because I live in a neighborhood where there's no sidewalks, so and I've got landscaping right out to the curb, but that's yet to happen yet. I'm just watching them as they work around the neighborhood further down the hill. I don't live at the top of the bluff, but I live part way up the bluff that's just east of here. So, and cable modems do DSP. They do modulation theory, high density digital modulation, which is also used in Wi-Fi. Voice over IP is pretty much a norm. Years ago, we had the MP3 and all the other audio formats, streaming, this, that, and the other thing. Wireless communications has been going on for quite some time. A statistic I got a few years back was 200 million phones per year over the entire world. It's probably maybe 300 million right now. I don't know. It's definitely gone up. Different types of subscriber loops, different types of fibers now, fiber networks. I'm really happy with fiber because I've taught optical communications. I worked in free space optical when I was first out of school. I tested at White Sands and flew up in space. Part of it and other parts were just tested from an air to ground. But optical has got so much bandwidth. Why is it possible to do that? Have you thought about that? What makes it possible?
Is it many different wavelengths you can simultaneously communicate?
That's part of it. You can have wavelength division multiplexing, but what makes it possible to send information from point A to point B is to have a band of frequencies available. So as you go up higher and higher in frequency, and light is just above terahertz, it's very high frequency, it's the fractional bandwidth that lets you get away with that. You're sitting on a carrier, like a wavelength carrier frequency, or wavelength is the inverse, right? Or related to the inverse. So the fraction of the bandwidth at a very, very high light frequency is gigahertz wide. And that means you can have gigabits per second of information. When you come down to lower frequencies, we don't have, and you have to maintain that fractional bandwidth of around, say, 10 to 20% or something in most RF terminologies, designs. You don't have as many hertz of bandwidth available. So it's very inexpensive to get it. At the lower frequencies, it's very contentious because the resources are all used up. I mean, we have all these assignments up to cellular and beyond that have been doled out to the users. You can't get a lot of bandwidth, so that's why 5 and 6G are going millimeter wave. But there's a lot of issues with that in propagation, but guided waves, fiber optics, works perfectly. So if you can lay down a fiber, you've got it. They have the so-called multi or single mode fiber, which doesn't have the dispersiveness that you'd have with the original multi-mode. Dispersion is kind of a killer because it distorts things, distorts the signal. An ideal coax is an example of a dispersionless medium, but single mode fiber is even better than that. And then, like you said, wavelength division multiplexing, so they lay down one light tube or one single mode fiber, then they can have a solid state laser diode send signals down that, and they can send slightly different colors of light effectively and have multiple channels. So I don't know how many fibers are going into the sheathing that they lay down, but does anybody know how many actual fibers are going inside each? The sheathing is like the outer jacket that they usually lay down first, and then they can push the fiber through that later, like cable pulling in your wall with a conduit. But if they can lay down dark fibers, is what they used to call it, they'd put more fibers in the sheathing and they would stay dark. In other words, they wouldn't light them up with comm links on them. Then that resource is already there and it's already in place, and then we can start, turning it up as we want more bandwidth. That has a future to it. I guess that's what I'm saying. It will eventually, we'll use it all up if we really need all that bandwidth, but it does have a lot more potential with all the pain and suffering you have to go through to get it down there. But a single coax, which is the way Xfinity was built, is not, we exceeded that capacity a long time ago. It's just technology limited, so fiber really sets the stage to go further. A new one that I can just sort of mention here is commercial aircraft Wi-Fi. Since I was flying overseas twice this summer, I didn't successfully use Wi-Fi because I didn't pay the extra money to United, but I was reading about a neat signal processing application that they're getting into for Wi-Fi in commercial aircraft. They get it from a satellite right now, and the aircraft has to track it as they fly. And they have multiple beams with antennas pointing in different directions that have to get fused with RF, to baseband and then distribution inside the aircraft itself. But now, apparently, I was reading an article that Mini Circuits published, something else I get in a news feed, that they're going with a beam forming solution. So they're going to have multiple elements, and they can form a beam so as they're traveling they can actually keep repointing it electronically. Well, each one of those channels then will have to have an RF to baseband digitizer and RF sock to down convert and get the data off it, and then form the beam with that to point it. So that sounded kind of exciting. That's a combination of microwave circuits and more signal processing. I say that like it's casual, but it's the easy answer, right? DSP and software, that it's just more software will solve the problem. I realize most of you think, oh, I can't get a piece of code to work. Software can't be the problem because it can be so frustrating, but it is what our world has turned into, right? We'll just write some software and we'll have it. Industrial, real-time processing of industrial and medical signals. There's wireless involved there. There's signal processing, whether it's wireless or wired, but robots and other information that industrial engineers would care about. Medical signals, certainly a really big thing. At the lower level, we have virtual instruments for PCs and DSP, and I use those when I teach the DSP lab. I use the analog discovery, for example, from Digilent. I generally have people buy those. I don't think I'm going to talk about it, but I think I have a link to it in a picture of it in the website for the lab class. Oops, I didn't make it bigger. Audio, internet audio streaming started a long time ago. It continues to be very big. So there's compression and decompression algorithms that involve algorithms as well. Home audio theater systems. You know, I didn't really realize how much TVs have changed in 12 years' time until we went and bought one. So we bought an LG, really nice 4K TV with lots of processing capability, more than what's needed today, but we decided to invest in their latest and greatest because although it's expensive, it has some growth potential in it. So it has Web OS, which is something I just learned about this summer, and that's pretty amazing. My sons like that a lot. I like it because I can listen to Sirius XM, which I have in my car, but I can use my subscription to do my internet streaming, and I can cast it over to the TV and audio very trivially. Most of you have probably been doing that for a few years now, but I just learned that in the last month, how nice the casting is. And of course the casting works good for the video part of the streaming as well. Other things that have been around and continue to improve is noise canceling and noise quieting. So we can add more gadgets beyond the standard noise canceling headphones. We can have things where we have quiet zones in a car and things of that sort with adaptive noise canceling. I've also worked with a local company, and this has kind of been something in my music playing, bass trombone, and sitting in front of a row of trumpets, or maybe having a drum kit with cymbals, taking my ears out. You know, I use earplugs right now, but I'd like to have something just for people who play in small groups in communities where you can protect your ears but yet still hear what you're doing. If I'm not careful, I will block everything, but then I won't be able to hear what's coming out of the end of my horn either. So I've worked with another company in town on adaptive, well, that's not, it's adaptive, but hearing assistive devices, more than just hearing aids, but things that are for people that have hearing problems. And sort of a standard problem that I would like to solve is called the cocktail party problem. Has anybody ever heard of that before?
Be able to block out all the peripheral noise.
Yeah, it's meaning you're at a party. You don't have to be drinking alcohol, but you're just in a group, right? And you want to talk to somebody in the back row, and you guys are talking amongst yourself, and I can stare at that person, but I just can't cut through the clutter. So have a means to, with some adaptive signal processing and AI type approaches or machine learning approaches. I had a student work on that. My ideal would be either adaptively, either to point your head or steer it from a device on your cell phone, you know, a touch something or another. You can just basically zoom around. I mean, the more sophisticated technique would be to have a feature that's associated with that individual, which you could learn quickly, and then you could spatially filter based on the characteristics of their voice. Because we're all a little bit different, right? And I have a very low-pitched voice, and high-pitched voices tend to cut through, whereas mine just gets lost in the clutter. I was born that way. I've had people say you got to speak falsetto, you know, raise to a high squealy sound, and that will cut through better. But at any rate, that's part of it. Or another audio thing that I worked on that you can do with Pi Audio Helper in the Jupyter Notebook is 3D audio. I played with that, where you can have HRTF, the head-related transfer function. And a head-related transfer function has to do with the spatial response of your ears. So you've got your right ear and your left ear. And it's a really cool mind game too, because we first learn about our HRTFs not knowing what a head-related transfer function is. But when we're an infant and you're hearing sounds, your brain is starting to train on how to spatially work. Now what I'm saying about that is if you're running or walking down the road and you hear a sound, like a car, which is could run you over, right? You can sense whether that sound is coming from, you know, back in that corner or up front, either side. Have you ever been amazed by that capability, assuming you hear normally? That we can process that spatially because we have a biomimetic hearing with our 2 ears. So if you can code that into DSP, which is what I've done, then you can wear headphones and have that transfer function, one for each ear. You can take a sound and spin it around your head if you want to. I've done that, and I also had a guy that worked with a camera system, so you could simulate, like in virtual reality, this would be the audio part of the virtual reality. You're sitting there and you're staring around, and the sounds are as if your head is really moving. So a neat demo he did was a cricket was somewhere in the room, and as you moved your head, you could, you would sense the crickets over there or something like that. And some of you might do this in game playing, because some game playing systems have HRT apps that you can select. Not your personal one, though. I had a PhD student work on how to estimate your personalized HRTF, which that would go to a theater scenario where you would have a little card that you would slide in if you were in a theater. You plug it in, and then you would listen and hear the sound spatially. That's just my view of how that could happen someday. I don't know whether that will happen or whether we want that to happen. Another good question. As engineers, we have to be ethically responsible. We can bring things on the scene that maybe are not things we should be doing at all. But I think there's things to be said for that. I mean, training and trainers and things there's an audio component to them beyond the visual. So I've been interested in that. But I have an idea for a device I'd like to possibly sell to other musicians like me that don't play in for fun groups, where we could protect our hearing and still hear ourselves play and other people in the band. It would involve wireless, and it would involve some both analog and digital signal processing. Biomedical, I already mentioned that, but there's a lot of things. I was mentioning hearing assistive devices, but diagnostic imaging, MRI, those seem to happen at a moment's notice. I'm having a hip issue right now, tendons and stuff, so I've had a couple MRIs done recently. So you go and sit in the tube and you get your MRI taken. Some of you have had MRIs already for one thing or another, right? You know what I'm talking about? Image processing, so that's signal processing in multiple dimensions. That's 3D. My wife had her back surgery. I went to her doctor's appointments. They had her MRIs. I got to see them many a time because 3 times she got interviewed doctors, but they could show you that stack up of the images. They went down her spinal column and see normal diameter of her spinal column, and then got down to her low back where the stenosis is, and just see that spinal column go down to about the size of a pencil, really narrowing. It's very pronounced. I mean, he would take us down through the stack of images and just see that cross section. And for me, they're looking at things in my hips, and one of the things they've been doing is imaging both sides, because when you have a bilateral situation, doctors want to know, well, this side's giving you no problems. Let's see how you look, you as an individual, compared to your opposite side. So that's very significant, and that's, again, image processing stuff. So ultrasounds are cool too. They're signal processing in that. If you've ever had an ultrasound done, like if you're a woman and you're carrying twins like my wife did, there was complications, and the ultrasounds helped out with that an awful lot. Could not see at that point clearly what was going on with one of the 2 of them, but today you probably can see a bit more with even that. Or I had an injection of some steroid in my hip to see if that would help, and it was guided. The needle was guided with ultrasound just to see where the tip was going before he did the release. And I thought that was kind of cool. It didn't hurt, but I was sitting there laying on the table with a local anesthesia, and the needle is long and it's going in, and some of you have probably had that done too. I've had it injected in my knee where they just push it in there, but the hip, apparently there's too much play, so they have to see what they're doing before they do it. pretty nice. In the beginning, we had military and aerospace, and that was probably over 60 years ago. Probably when I said Oppenheim and Schaefer started in the late 60s and 70s, that's when the military was starting to use it. You know, space program gets the newest and the greatest military, our defensive systems get all the new technologies, and that's been the impetus for a lot of things that get to happen. I'm not going to walk through this because I've kind of already been rambling on it, but any questions on any of these applications that I've gone through? It's unlimited right now. It's electronics from the outsider's point of view, but it's different types of electronics. Digital, signal processing electronics, analog electronics. I mean, signal processing engineers work together with all the other types of electrical engineering in terms of chip level and coding and so on. So this, if it will rotate, this is what was before I left. We're sitting right in this class, Modern DSP, right here. This top row is the undergraduate core background. The signal processing lab that you see right here is what is offered right after this class. And that board that I passed around is a new board that I would like to introduce over the current Cortex M4, which is not in production anymore. But even so, the basic idea is the same, being able to process signals in real time and write code to do that, take measurements using lab equipment, take measurements like with logic analyzer to see how much time you're in your interrupt service routine. That's kind of the big thing with real time. Can we give our DSP algorithm, do we have enough time to process our signal sample that comes in before we have to ship it out again? And that's 1 over the sampling rate, that's the period. So we have to be able to keep up with the real-time flow. And that's, you get exposed to that with different applications in the lab. I'm not sure I'm going to want to jump and look at the website for the lab today, but it's up there, and I'm going to go up to the lab right after the lecture today and see if any of you are interested in. There's a graduate student that's going to teach it. I'm going to help coordinate it. I don't have an office in the building except up in that CommDSP lab next to the lounge upstairs. So that's where I'm going to go right after class to talk about any and everything. Last year the lab did not get offered because only one person signed up. I'm trying to do something to make it different. But you know, it's up to you if it fits your schedule. It's a 1-credit lab. It's one of the labs that you would take for breadth. Remember your schedule. I'm probably saying something that you're not familiar with. Go over here for a second.
The engineering technical electives labs requirements, is that what you mean?
Yeah. I'm already in the web browser, never mind, I just need to go back up here. I need to go to home. This is something I created a long time ago, but it tells the story. What I'm talking about is, this is undergraduate education in EE, in computer engineering, starting at the bottom. It's EE is what it is, it's not computer engineering, but work your way up, and right now we're at the breadth lecture level. If you're taking it as an undergraduate, you're taking 5650, and that is right in here. And then the breadth lab is right here. This is the COM lab, and then there's 4680 is the DSP lab. And some of you were mentioning microwave measurements. That's over here. That's in the same stack. This idea of the stack up. Is that a good terminology? Because it's my model here was you're building a house. You take senior seminar and senior design at the end. These are your electives, and then you graduate. Built with PowerPoint widgets, so it's the drawing doesn't maybe look super snazzy, but So that's what I was talking about with that. So back over to here. So other classes that could be offered, and apparently I'm going to be doing an independent study for at least one graduate student in Comm Systems 2. That website is not on my new website yet, but all the videos have been pushed. So I'm going to be teaching it remotely, and that student's coming to meet with me after this class too. He'll watch the old videos. I'm going to eventually be moving over other websites to the new site. I just have to do it myself, and it's just for the fun of it. I mean, I'm not a faculty getting paid, but to me it's important because my website is very valuable when I'm working in a company. I can point people at resources and share resources, and I've come to rely on it a lot. Is that believable? I mean, my lecture notes are kind of like how I read. I go look at my notes, they're there. And if they're handy on the internet, I can point people at it. So, I mean, I have the originals on my computers, but it's faster to just snag it from the internet. So this would normally be what would follow. There's also been a 3-credit real-time DSP class that has been taught generally in the spring. Don't know if that will ever be taught again. I'm contemplating saying I would do it. It's a 3-credit version of the 1-credit course that's offered in the fall. It's got different labs, it's got different depth to it. Possibly I would agree to do it under the same scenario that I'm working in right now. I think a new faculty would teach this class no problem. Real-time DSP class probably not as readily. So I'm contemplating that, but the problem is I have to not want to travel during the semester. And right now I can't travel because of my wife's surgery, but next spring, you know, she didn't get to go to Scotland, my son did. She said when I came back, I get to pick where I want to go, and so on and so forth. So I'm waiting for her to say, this is where I want to go. I realize she's still recovering from surgery and she's not really thinking about that, but that's going to hit me, and I'm excited about it actually. Very excited about it. I don't know where it's going to be though. Maybe it's Iceland, I don't know. So these were just other things in the suite. They're going to be interviewing faculty in the next couple of weeks. That's what Drs. Plett and Trimboli were telling me when I went to lunch with them. So we can talk about that on Slack. You know, we can do calls. I mean, all these things are possible. So I don't have an office here. I'll go home after lunch. I'll hang around here. But if you make an appointment with me on Slack, and that is, that's pretty important. To not think that I'm not available would be a misunderstanding. Let's see. That's right. I'm getting myself confused. I'm on the web browser. If we were to go up over to here, at the Jupyter Notebook, which I was in. I got disconnected, which isn't what I was expecting would happen. On the home page here, I have this graphical depiction, and this used to be my life here, where this was all filled in with meetings and graduate students. So right now it looks like I'm pretty lame, but I'm not getting paid very much money either. So, but that gives you a graphical view of at least how I visualize this day. If the lab rolls on, I will assist that person, and then I'm in here. So the rest of it, as this bottom tells you, is Slack would be preferred. I am availing my personal cell phone. I'm not super excited about it. Slack, I think, is better. I would consider WhatsApp, but I was thinking about that last night because that's how my family communicates, and that's how you communicate when you're in Europe, or at least that's worked really well. But WhatsApp requires you to use your cell phone number, so I'm not really keen on that. I would rather just stick to Slack, and if it's really vital, but Slack is the best. Like if you can't make it to class, just Slack a message to me rather than go to a text. Texting is ugly these days. The political junk that you get. I don't know if you get it, but I certainly get stuff. I don't like it anymore. Anything that we've created as engineers for good, wholesome purposes is turned bad by the society around us, typically, right? You know what I'm talking about? I mean, there's all kinds of bad things on the internet. It's just, we're trying though, and we're not saying we're not going to do it, but it does happen. So back over to here. Okay, so what the course is about is nuts and bolts of one-dimensional discrete time signals and systems. And it could be, you know, n dimensions. It could be 2 dimensions if it was images, or 3 dimensions if it was like MRI images, you know, 3-dimensional bodies and things. But that's more complexity than I want to handle. 1D is good enough. You can extend it to n dimensions in your reading and so on. So analytical skills, introducing specialized applications is secondary, but the second project will be an application of some sort. I've got several projects canned up that use Python that work well. The good news is most everything parallels continuous time signals and systems, and as a matter of fact, one of our chapters is on basically the A to D and D to A. It's the converting back and forth, and that's where we do multi-rate sampling. And multi-rate sampling is also a new feature. I mean, this has a lot of the same topics from 2610 and 3205, but you're more mature now. I mean, I used to teach 2610. People were so weak when they came into that. Their math was just coming into focus. Physics maybe wasn't done. I mean, you grow up so fast, and I remember people, how much they changed in just one semester of 2610. And you can think back, probably. Would you agree? I see you're nodding your head. You don't even want, I mean, the babies like, the adult children like to talk about how they acted when they were babies? No, right? You just don't, it's not something you want to talk about. Your parents are excited to talk about it, but I remember my parents did the same thing. It's like, don't remind me of that. I just don't want to think about it. But the same thing goes with college. I mean, you learn so much so quickly, and you just want to keep forging forward, which is what you need to do. But so there are things that you will do. The problems will be more intense, and will bring in new features like multi-rate processing. No DSP system has an A to D that ticks along at 44.1 or 48 kill samples per second. You've got multi-rate processing. It's just inherent. It's inherent in the A to D converter, which is using a delta sigma. We'll talk about what a delta sigma A to D and D to A is all about. That's a multi-rate processing block right there, and it's on that board I passed around. You don't worry about it, but it's running there. There's a higher rate clock, and it's multi-rate DSP is just there. It's not something that you can't cope with, and we'll learn about that. So that's, I guess, what I was saying here. It's what's going beyond that. And the Oppenheim and Schaefer book is very good because it's very hard. I guess I'll say it. Hard in the sense that it takes you to the limit, but it's got the problem set up in the book where it goes from low level, medium level to high level. So I give mostly low and medium level problems, and then I'll give maybe 1 or 2 of the high level problems each assignment. So you get something like, if you're a graduate student, you'd be more thriving on the harder problems. If you're an undergraduate student, you would be challenged more with that. It's just, but it has to be that way because it's a dual-listed class. And since I'm throwing that out there, what is it that the dual listing does? If you're taking it as a graduate student, the projects that we have in this class, you have to work on solo. If you're taking it as an undergraduate, depending upon which project it is, it can be solo, 2, or a group of 3. So you have some camaraderie options thrown up in there if you're taking it as an undergraduate. ever since COVID, nobody really wants to work in teams as much because everybody was trained to work in isolation, right? So if you're a graduate student, you're not fazed one iota by this, I don't believe. You like working alone probably, and you will work alone, and you probably thrive. A lesson I learned during COVID was the graduate students I had in the real-time DSP class bought the hardware, had the board, they could do everything at home, and they did have partners, but they were living in their apartments because most young engineers that were in graduate school with me then, they lived in an apartment by themselves. They couldn't do anything. They could work homework and they could work projects, and they were working really, really well. They were probably lonely, but they were getting more work done, and then they used Slack or whatever to communicate for their teaming. But it was the undergraduate students that were totally lost during COVID. They were watching my lecture video. They were doing the lecture like this interactively, laying on their bed with their cell phone, and that did not cut it. You know what is that making sense? It was very casual, and they didn't do very well. It was an experiment, right? I think. It was an awful experiment in a lot of ways, though. It was hard. I thought it was really hard, but it's behind us now. So what are some of the unique things I've already mentioned? We'll spend more time on A to Ds and multi-rate, sigma deltas. We'll talk about that. So there's some amazing things that go on there, really amazing, from a semiconductor developments and things that have happened over the years. We'll do multi-rate processing, which plays into software-defined radio, factors into software reconfigurability, and then a big thing here is this one, discrete random signals. This is a topic that if we were to go back and look at that slide with that org chart, essentially, it says you take probability and random variables as an undergraduate, and then you kind of don't do anything more with that. You take probability, random variables, and statistics, right, in that class. But there's another dimension to that, and that's called the random process. It takes it up one more notch. So you're going to get introduced to discrete time random processes here, which has underneath it random variables and probability. But what do we do when we want to model a signal as having a random element to it? It becomes a random process at that point because it's got time, or it would be space if it was a multidimensional signal. But just take a one-dimensional signal, it will have noise, or it will have some attribute of the signal that is randomly varying, and that makes it a random process. It's big and sophisticated, but it's a math tool that's useful for characterizing things. Nothing is ever done, and this is contrary to common belief, I think, as an undergraduate. Nothing is done to make things complex just to make your life bad and hard, right? Why would we introduce math concepts that don't lead to something that we can actually build and understand how to make it? So the random process is a good example of that. There's a bunch of math definitions and things that go on, but it leads to understanding quantization effects, let's say, which is a reality when you have finite precision arithmetic, and statistical signal processing, which nominally is a follow-on. It's very important there. And statistical signal processing has a lot in common, but just a different title, with machine learning and some quote, artificial intelligence type ideas. They're related to each other. The traditional name in EE is statistical signal processing now. And it has some of the exact same elements that you find in machine learning, and it's based on the use of statistics and then how you capture your information, your waveforms or whatever. And I'm also building simulations where we do have noise, like in comm signal scenarios, if I was to go that route. And even in audio with the Jupyter notebooks, you'll be adding noise in, and you'll be listening to things, and you'll be putting GUI sliders in there that will change filters or change the intensity of the noise, and you'll be listening. I have you do some listening experiments where you adjust things on the fly and listen to them and get a flavor for what these filters are doing. That's very cool, but you are going to have to set up some software and wade into the waters kind of deep with the Python open source software. But I don't think, I've been doing this for 10 years now, at least. PyAudio maybe not quite 10 years, but I don't think you're going to fail at it at all. You're just going to do it, and you're very used to installing software, right? And I guess since I'm mentioning that, and we're about to talk about that, what type of operating systems are you using, just so I'll be aware of how I can support them? I use all three in my work. I didn't use a MacBook at my work, but I have one at home. The company I'm working at now issued me a MacBook, but in my previous job with Augustus Aerospace, I had a laptop that did Windows, I had a laptop that did Linux, and then I had a workstation that did Linux. So Linux is just a little bit more challenging to work with, and it's not essential for here, but you can put the tools all on Linux if you want to. Windows is fine. Mac is also fine. I'm assuming Windows more, and I'm perfectly okay with that. I'm running Windows right here and just updated this to Windows 11. So, but I just want to know so I know what mix I'm expecting. What are,
I use Mac.
okay, okay, Windows, okay, okay,
Controversy.
okay. Well, I'm mostly using Mac and Windows right now, and I'm very good at it, and the PyAudio stuff works really well with both of them. You'll just have to make sure I know what it is your issues are, because they each have little idiosyncrasies. No operating system is perfect. No operating system, in my view, is the end-all to everything, because you've got different things you have to do with them, and that's what I think is the driving factor. Linux probably would be my favorite, but you don't communicate very well with a team on Linux typically, like if you have to do Office stuff, Microsoft Office stuff. So, but it has a lot of good things about it. I tend to like to use Windows subsystem for Linux now on my Windows machines, and I run WSLG, which is the graphical stuff, so I can run some Linux apps with graphics and even talk to USBs, like for software-defined radios from another laptop I have. It got put on this machine, but I haven't done anything with it since it was put on last week. So we're going to be using tools, and I'm advocating for Python. Julia is out there. I'll introduce you to Julia. It's faster than Python. It's even faster than MATLAB. I like Python, though, because it's open source and it has a lot of more modern features than what MATLAB has. I was forced to use MATLAB at this previous job because the older guy I was working for, we're probably the same age, but he seemed to be older in his mindset. He liked using the telephone a lot more than I did. You know what I'm saying? People don't talk on the phone that much anymore. They like to message or do other things, but he had to know my home phone number. The first week I was working for him, I said, why do you need my cell phone number? It's because, as I learned, he wanted to be able to be in contact with me on the telephone. How many people do you associate with that are like that want to talk to you on the phone? Maybe your wife, but even my wife likes using iMessage and all that. I mean, we do all that stuff, but just an interesting thing. So he used MATLAB, though, is what it came down to, and I got back into using MATLAB just fine. Once you know Python, MATLAB and Julia are very, very similar. But the thing about Python is I learned 2 years ago, I tried to push into Julia a little bit, and I may still try it. I also pushed into C and C++ in one project problem. I'll be debating that in my mind. You know, how many of you know anything about C++? So I had a mixed problem where you developed in C++ with objects, and I had a lot of the code supplied for that. But the key to that will be Visual Studio Code, which I like using as my editor. So that handles everything, and I have stuff for getting all that stuff set up on your computer. So Julia is fast. They call it the two-language problem, but it's the language is a little bit pickier than Python is, and when I first started pushing people away from MATLAB into Python, they didn't like that because it was too much like real software, and it is, but you get more for it. The more you put in, the more nuances you have, the more power you get, and it's a very popular language right now. It is probably the most popular language, I think, and if you don't know enough about Python and want to learn more, this is an opportunity to do that. So is everybody good with using Python? All of you have probably learned more than people had in the beginning, but is anybody never used Python? How about Jupyter Lab? Okay. But Jupyter Lab type features are available.
I think it's not used.
What happened? The projector died. Why did that happen? It got quiet in here though. How do I turn it back on? This should turn it on, right? Okay, this is going to change the rest of the class, which isn't that long. Let's see, what number do I dial? 4357. What's that? Can you go up there and manually try to turn it on? There's nobody from OSHA looking at you. Standing out.
I will press the power button. How's that sound?
Yeah.
I like that.
Green is good.
So it's coming back on again. Okay. You might have just had a, all these projectors have timers on them where there's maintenance that has to be done, and then maybe there's something that says maintenance. Why did it just turn off though? I didn't pause any longer. Okay. This is what I'll do though when we get into trouble. I will call them and make them come up here and help me, because that's what they're there for. They get paid to do that. I don't know what other professors have done for you, but I don't hesitate. I'm just like, our time is valuable. So, okay, I'm glad that happened. And I didn't even take my microphone off. Okay, so I was getting ready to do what you did. I was going to get up there and stand up and press a button or something. So in the real-time side, we use ARM Cortex. That's what the lab does. ARM is a very pervasive processor core, so it doesn't matter the vendor. That new board I passed around is ST Micro. We're using one from Infineon, which bought Cypress. The board is Cypress, but Infineon is here in town. You could go work for them. I mean, I'm just saying they're a semiconductor company. ST Micro is in France, so you wouldn't go work for them unless you wanted to go move to France or something. And I already mentioned Verilog, VHDL, and all that kind of stuff. So working with the boards is a lot of fun, and that's what the lab does. So we're not going to do that here. I just brought up some of the things. Xilinx is also other options with their system on module, which I haven't really played with that. I got one to practice with before I left, and it's just sitting there because I've tinkered around with that board in the back. More than anything else in terms of developing some things. So the computer projects, there'll be two of them. One is kind of core stuff that it'll have you do, and it has the Pi audio things going on at the end of it. It's to bring you up initially with writing code in Python, so it takes you from nothing to something. But I'm not going to wait that long. I'm going to take you to something immediately. I mean, the very first homework assignment, you're going to be trying out some Python. If you were to take the lab, the very first lab is working in Python Jupyter, just so you are coding something. But then it introduces you to the real-time DSP. I'm thinking of changing the labs out. The second lab right now is an audio processing lab using Python, but I'm thinking of just adding another real-time lab because that board in the back has got 2 microphones on it, and I've gone through the model of the 2-element audio array, and you would just play with that in the lab, where you can do some spatial signal processing with 2 microphones. Haven't decided on that for sure. The lab that I'm contemplating pulling out is a lab that you learn about something called butt splicing. And butt splicing sounds like a bad thing, but it takes you back to audio tape, where you would have audio tape and you would, if you wanted to splice 2 pieces of audio magnetic tape together, you would literally butt them together and put a little joiner on there to hold it together. It's not what you do in that lab. You'd literally take the long vector of signal samples and you can parse things in and out and do the equivalent of butt splicing. And what you experiment with, it's still kind of neat to talk about it though, is you can slow speech down or speed speech up, but not change the pitch of it. And there's other tools out there that do it more sophisticated, but this is to give you a flavor of how easily you can do some DSP. Do any of you ever do that? If you watch videos on YouTube, you can speed things up or slow them down. So that's the idea, because the speaker's voice would go up in pitch or down in pitch, but that's not what we would like, right? You want to sound like a male or a female voice and not have that problem. So that's DSP again, right? It's probably sounding like a broken record, but DSP is just pervasive. It's just everywhere, which makes me think about something with HD TV and 4K TV that is annoying, and that is the speech signal and the video signals sometimes get out of sync. Why is that? Have you ever thought about that? Does it annoy you when that happens? It annoys me a lot, but I know the design of television signals was audio and video have always been carried in different parts of the waveform. So in the DSP domain, it's possible with the buffering and things that go on, I guess that the switches and the routers, et cetera, that everything flows through, that parts of the message get out of sync. I have to ask somebody that would explain that to me, but during the Olympics, it happened a few times, and it can happen just about any type of program, right?
For me, the video always comes first. If they're out of sync, the video is a few seconds ahead.
Yeah, I guess maybe that's right. I don't watch much TV. My wife and my sons like it a lot, but I don't. But that's a good, that just ran through my brain. So you want to work for a company that can help solve that problem. I think it's a router. It might be the way the information is carried through the network that it lags. And like you said, the videos is got related to comms and DSP is the concept of the network stack, of how networks are put together, and in a stack of networking and packets going through a network, you've got something called quality of service. And quality of service has 2 main attributes, if you think about it, in networking. One of them is latency, and the other one is throughput. How much total throughput or bandwidth do you have? So the latency is the one that's getting messed with, and the quality of service for video is more demanding to hold all the info for the picture, so maybe its quality of service is 1 notch higher, or 2 notches higher in the network stack for priority than the audio is, because it's less information. But that doesn't really excuse the buffers from not being able to sort that out. I think about that, but I shouldn't talk about it here because I'm taking valuable time, but that's something that somebody has to think through, though, how they travel together and they're tagged together. So the projects, you'll also do a project on multi-rate processing, then you'll use Pi Audio Helper, and Scikit DSP-Com is my Python package that's up there in the cloud. And then there's a capstone kind of a project, and I have a couple popular ones that I do there, and I'll talk more about those later. We've already been talking about the board from the lab, and then I mentioned statistical signal processing. The syllabus, we should try to go through that, and what do I have after that? The syllabus is on a separate sheet. I just have it embedded here, so it's all in one package. But okay, I'll go through these instructor policies, and then we'll go look at the syllabus a little bit. I want homework papers when they're due to be due by noon on the due date. So in other words, if homework was due today, I wouldn't want you to be sitting there during lecture figuring out how to send it to me in Slack, because that's kind of like I'm defeating my purpose in lecturing. But I will give you the opportunity to have until noon of that day. So if you leave class and have a little bit more tweaking to do, and just push it over to me. Second bullet there, though, handles extenuating circumstances. If you're traveling on business or some other activities, inform me beforehand. And I'd like to know a day before, but if I'm getting a Slack message early in the morning to know something's gone wrong, or something's gone wrong with your transportation, or all kinds of things, I just want to know what to do, because I put up solutions as soon as I can for homeworks. And you're going to have a password that's going to allow you to get into the solutions. And I just want to maintain integrity. And I will put people on their honor. An individual that is going to be late, I will eventually put the solution up, and I'll put that person on an honor code. Absolutely, you can't look at anything until I get your paper. And then we'll negotiate on that. Can I turn in part of the paper and get partial credit? Of course you can do that, but I'll still need to know about that, because I have to be fair and reasonable to everybody. I try to go with a straight scale, but curving happens, and that's why I keep you informed throughout the semester with histograms. I'll give you snapshots from homeworks, and then homework aggregated histograms, exam histograms, and then aggregated histograms of homeworks and exams and projects, and then sort of projections. I'll give you a histogram that will not have certain components in it, like the final exam or the final project. So I'll be able to give you a histogram that tells you where I think we're headed and what I think might happen. You know, like what happened after the final is finally thrown in there. And these are things that I think all of you do. Students have always done this. They know what they're getting, and they know that this factor is in the syllabus, and that's why we have to look at that. And they'll just be wanting to know how they can guesstimate where they might end up. And of course, it all depends on everybody else. I can't say exactly where the lines will be drawn, because that's not really known until I see how it all comes out. If I give problems on an exam that are harder than they should be, everybody will be influenced and maybe not do as well, so then I have to lower the thresholds. If things are too easy, I have to go the other way. So, but I try to keep you informed with these histograms. Does everybody know what a histogram is? It's pretty basic, but it's a very useful tool for me. And don't think because you're an undergraduate student that the graduate students are going to be always scoring and doing better. It doesn't work that way, because the graduate students have their reasons why they maybe struggle, and the undergraduate students, you have your reasons. It's very interesting, but generally the highest student can be either a graduate student or an undergraduate student. Generally there's one of each. Undergraduate students say, we have all these classes to do, we can't put enough time in any one class. Graduate students say, we have all these other life things to do, like their jobs. We can't put enough work in our class. So you both have valid excuses, and that tends to almost equalize itself out. The only thing that can't go away is maturity, and I don't know your maturity. Everybody's handles things differently. regardless of age, I think. I'm not a sociologist, though, but I'd like to think I've learned a few things over the years about things and students, things that happen, right? Especially if you have a family, there's all kinds of dynamics. I mean, what is it to your life has seemingly got three pillars to it if you're a student. One pillar is you're standing on trying to get your education. Second pillar is you're trying to manage your job. Third one is you're managing your family, your children and your spouse. All those things are vying for your time. True? I didn't get married until I was here as a professor. I met my wife when I was here at a church retreat. So I didn't see how I could make it work. I was very selfish. I just spent my time going to school and didn't have any other constraints. All of you are different, though, and I have to respect that fact, and that definitely factors into how you lead your life.
You got twins.
What's that?
Then you got twins.
Yeah, I know. I didn't teach class that day because it was an emergency C-section that I went down to the hospital for. But my wife was already down there. She was on preterm labor. She was on, what's that drug they put into your body to make contractions subside? Pardon me? I'm trying to remember. What did you call it? No, she wasn't on that.
Prevent them or encourage them?
Prevent, to slow it down. With twins, you try to slow it down. At any rate, she was whacked out on that a lot, and she was down in the hospital already when they finally made the decision that it's got to happen now. And they were born very early, so that was a whole new scenario. Okay, homework solutions, I already mentioned those are going to get posted. Screencasts will get posted. It'll take me some time. I'll probably work on it this afternoon. Don't know what I'm going to get with my mic levels right now. And we decided we're going to do a separate YouTube channel for that. And old exams will get posted with password keys, with solutions prior to the exams. And we'll be able to go through those in class, and you'll just have that stuff available. I have a huge inventory of old stuff. So this tab had the syllabus in it. So a lot of this we've already gone through. My cell phone's on here, but I'm just really leery of that. So be very respectful of that. Slack is what I want you to think of as your first go-to. You won't be able to find me here in the building. You're going to have to resort to that after these days, and they want to pay me more, but I've got stuff to do. And not only that, my wife can't do a lot of things right now, so I'm the meal person, I'm the dishwasher, I'm the laundry person too. I found out that takes a bit of time to do all of that. I don't fold clothes really neatly though, but I do get the job done. So we talked about the book, and if there's something more I have to do, you're going to let me know on that. These are links in here so that you can go to things. Julia is cool, and I originally thought I'd push hard on that, but I learned 2 years ago that most of you weren't interested in Julia, but I still will demo it to you. So the most important thing here, though, is this I call the contract. This gets referred to as we move throughout the semester, but homework assignments, which will include some computer work to do the modeling. Python is the best, probably 25%. Final computer project. Or computer projects, I guess. I should say together, because the computer projects are stacked together. 20% or 15%. So I'll bring the two computer projects together that you work on and weight them with a particular ratio, but then at the end, see if that works. At the end, 2 and 3 come together in a balancing act in my Excel spreadsheet. The exams are each worth 15%. First one is in class. The second one has always been a take-home. This year, because I noticed the university is doing away with any class meetings during Thanksgiving week, it changes my dynamic slightly, but it really doesn't change it at all, because a Wednesday class never met during Thanksgiving week anyway, right? Those of you that have been here know how that worked. But the take-home exam is generally given out, posted up on the website on Friday, and then you would generally turn it in on Tuesday of Thanksgiving week. If that poses a major problem that you can't do that, we'll have to talk about it, because I just don't want to give that up right now. I mean, I don't want to say you don't have to do anything. I could say the take-home is due Sunday night, and I could do it that way if I wanted to. The take-home is just an option to redistribute your effort, is what I'm really trying to do with it. You have more flexibility in how you work on it, but and maybe I'll give the take-home out on Thursday. But I just want to have that different form going on. There will be some computer simulation and modeling in it too. I have lots of hints. I just give out a lot of stuff to do that second exam, and generally people do really well on it. Final is in class. It will be in here, and now this red connecting line there is to say that when I put everything together in the spreadsheet and I'm looking at what is going to give you as an individual the best. You know, if you work on a team on the projects, your team shares that score. So if each got, say, 90, each person on that team would get 90. But that would go into that number 2, the computer project category. And then I allow this swing factor, so you can push up higher in the project grades and drop the final exam lower to 25%. Or if you want to do, if it works out better for you to dial the projects down more, and then you dial the final up more. Or if you're a person that just everything comes together in the final you just do really, really well on, you know, that can be good for you too. All those things vary so highly, right? As I've learned over the years, some people do really well on finals, people that have never done that good, and then that option might get chosen. Most people, though, do well on the projects, and they end up with the final only being about 25%. So that's kind of a nice thing to know as well, that option is there. So the rest of this is the topics. Well, I'm not going to talk about the topics because we're pretty much out of time. Do you have any questions? I'll take opinions, and if you don't want to speak right now, you can go direct channel me on Slack to know what you're thinking. And I will, if you look at the first homework assignment, I will also, that is over here, I will be taking questions, and I'll be pushing out a hints page eventually here too. So I'm nominally pushing for September 11th. That's an anniversary day, right? I was here when that happened, so I definitely remember that. Had a PhD student from Thailand who was very freaked out by what happened that day. Most of you can't remember that well, but it was, yeah, it gives me some chills just thinking about what was going on here in this building on that day. At any rate, the assignments are in here. Some rules are in here. And then there's already a Jupyter notebook out here that you can use that has some hints on it and some other hints that I'll give you. If it looks like we're not going to make that day, we'll see what happens. We have lecture next week, though. Even though we have Labor Day, we have to get our act back together again and wake up, you know, to be back at work again or back at school on Wednesday. Well, how is it working next week anyway for the campus?
Yeah, I think it's just Mondays.
Just Monday? Okay. It used to be Monday and Tuesday, and then during Thanksgiving week, Monday and Tuesday would meet, and then Wednesday, Thursday, and Friday would not meet, so that formed a complete week off. So now it's different. That's interesting.
I think they have, I don't know if they coincided fall break with the Thanksgiving. I'm not sure.
I'll point you at other course materials, though. Some things that are down here. This this is everything about my package. So as you start using Scikit DSP Com to help solve problems in Python, there's lots of examples up on this, so that's very good. In terms of getting your computer set up, let's see. Why can't I see that right now? I've been working on this so hard I forgot where I put the links to this.
I think you put it on the syllabus.
Well, I did, but it's also in here. I'm just, my brain is a little bit fried right now. I just redid this yesterday and pushed it back up here again. Okay, here it is. So I'm going to steer you away from install Julia and Python and Jupyter Lab together, and instead I'm going to push you at setting up a virtual environment under Miniconda. And the first part of this is how you would work it in the lab, but as you do here, there's a section on your own PC, and then you'll be able to get everything set up, including Scikit DSP Com. And then if you were going to run anything, you'll end up having a Jupyter notebook, something like this. And I have examples of these notebooks on the website, but this is the type of thing that you will do. You will shift enter here. I'm running a cell, and then I can put my math embedded, but down here I'm going to create an array. I think I did that up here. I don't know, but at any rate, this is the type of thing you might do to produce some output. We'll be talking about the delta or impulse signal, but you're going to get into this, and we'll be going through this next time more. I'm going to go up to the lab right now. I'm going to stop my recording.